In this lesson, we'll cover solving exponential equations, but let's start simple with 2 to the x is equal to 8. We could probably just guess the answer, but I want to introduce a strategy that we can use to solve more complicated exponential equations. That strategy is to make both sides have the same base. So I'll leave 2 to the x alone, but can we rewrite the right side so it's 2 to a power? And it turns out for this problem that we can. And the reason is, if you take 2, raise it to the power of 3, well, that's the same thing as 8. But basically, this solves our equation because if the base is the same on the left and the right, you can ignore the base, essentially canceling it, and then just set the two exponents equal to each other. That is, x is equal to 3. This is a lot of work for this very simple equation, but again, it's the strategy I want to focus on. Rewrite both sides so they have the same base. And once they do, you can equate the exponents. So certainly this is true, right? You can say, well, is 2 cubed equal to 8? 8 is equal to 8, so this strategy does work. Let's try it on a more complicated problem. All right, so let's solve this equation. 2 to the power of 3x minus 4 is equal to 32. My strategy is to rewrite both sides so the base is 2. Well, on the left, we have 2 to the 3x minus 4. That's fine. But 32, that is 2 to the 5th power. So 2 to the 5th is 32. Because the bases are the same, I can now take the two exponents and set them equal to each other. To solve for x, I can add 4 to both sides of the equation. I'll then divide both sides by 3, and we get that x is equal to 3. In example 2, same idea. I want to solve this exponential equation. Okay, I think the base I'll use for both sides, again, is 2. So on the left, I'll leave it as 2 to the 1 minus 7x. Now on the right, okay, I see a fraction. So I'm already thinking, okay, we have to have a negative exponent. So how would you get 1/8? You'd have to put 2 cubed into the denominator. So I saw the 8, it made me think 2 cubed, but the negative puts that into the denominator. So if we want to now solve this equation, the bases are the same on the left and the right, we can say 1 minus 7x is equal to negative 3. I think to solve this one, I will subtract 1 from both sides of the equation. I'll divide both sides by negative 7, and my answer is x is equal to, the negatives cancel, and I have 4 over 7, and that's my final answer. Now, what about this equation, though? Sticking with my base of 2, 2 to the x is equal to 10. Can we use this strategy of saying, all right, well, I'll leave the side as 2 to the x, and I want to write the right side as 2 to a power. Well, 2 cubed is 8, so I can't use 3. But if I try 2 to the 4th, that's 16. I think the issue with using this strategy is that I can't think of a way to change this side so it's 2 to a power. If that happens, we can use another strategy to solve for x, and that strategy is going to be to use a logarithm. And we can use either log base 10 or the natural log. I think those are two good choices. Technically, you can use any logarithm that you would like to. I'm going to stick with these two just because they're the most common, and there's buttons on the calculator if we would like to, let's say, simplify or approximate our answer. Okay, so what's the strategy here if you want to solve this thing for x? So I won't do this, but the first step will be to, let's say, take the log of both sides of the equation. So that is, I'm going to apply the logarithm to both sides of my equation. It'll look like this. I take the log of the left, and I take the log of the right. Now, why would this be helpful? In the previous lesson, we saw that if you have an expression like 2 to a power, we are allowed to remove the power from this exponent and put it in front here. So this left side is equivalent to x. times log of 2, and that's equal to log of 10. This is a very important property of logarithms, and it's nice because it changed our exponential equation to a linear equation. Log of 2 is a number. Log of 10 is a number. X is something we have to get by itself. Since this is a number, we can divide it to both sides of the equation. So divide both sides by log of 2. I mean, it looks weird saying log 2, but that's just like if there was a 5 and a 5. You can completely cancel them. You have x entirely by itself, and on the right you have log of 10 divided by log of 2. That is an exact answer. If you want to approximate it, this is where you could type it into a calculator. So I'm going to try that out. Like, well, what is the answer approximately? I'm going to enter in log 10 divided by log 2 and see what we get. Maybe I'll have to round it to a couple of decimal places. Okay, log 10, log 2. Okay, it's about 3.32. It goes on, but this is a decent approximation. By the way, I was expecting the answer to be bigger than 3 because 2 cubed is 8, but also less than 4 because 2 to the 4th is 16. So this is a reasonable answer, and it's an approximate one, but this is the exact answer. All right, let's solve this exponential equation. I'm not sure what strategy we can use first because, well, for starters, this is 3 here. I don't really know how to write this as 5 to a power because, well, this side has some extra stuff attached to it. So I think my first step is going to be, well, why don't we divide both sides by 3? What that will do is cancel the 3 and at least get me the 5 to the x by itself. So the left side is 5 to the x is equal to, I can do that in my head, 24,384. If I divide that by 3, you get 8,128. And we have 2 strategies. I could write this side as 5 to a power and then just set it equal to this x. Nothing's jumping out at me. I'm not thinking that's going to work. So I'm going to use my second strategy of I'm going to take the logarithm of both sides of my equation. As I stated before, you can use any logarithm you want. Probably sticking with log base 10, the common logarithm, or the natural logarithm, log base e, is the way to go. Since I used this in the last example, I think I'll use the natural log here just to see if anything looks that different. My next step is going to be to take the natural log of both sides of my equation. So on the left, I'm taking the natural log, and I'm doing the same thing on the right. So that's the natural log of 5 to the x, and then the natural log of 8,128. Let's see, in terms of simplifying this, the reason for taking this approach is we have a property that for any logarithm, if you have an expression to a variable, you can remove the variable from the exponent. The left side of this equation is equivalent to the natural log of 5 times x. And on the right side, we have the natural log of 8,128. So this whole symbol is just a number. So is this one. In fact, you can enter it into a calculator. If you want to get x by itself, the next step is to divide both sides by the natural log of 5. And when you do that, on the left, they cancel. It leaves you with just x. And on the right, you have the natural log of 8,128, all divided by the natural log of 5. That is the exact answer, whatever that is. So maybe I'll type this into my calculator and see what we get. So I'm going to enter ln 8,128 divided by the natural log of 5. That is about 5.59. So this is a decent approximation to the original equation, the solution for it, and this is the exact answer. In our last example, we're actually going to solve a logarithmic equation. So this is not an exponential equation because it has logarithms in it, but let's see if we can figure out what the answer for x is. So here we go. 2 times log of x is equal to log of 32. Let me rewrite that. So 2 log of Oh, and I'll put some parentheses for emphasis. This is equal to log of 32. I mean, it's tempting to say, maybe we could divide 2 to the other side of this equation. And that's a valid step, but that doesn't get x by itself. So why not try a different strategy? If this 2 were not here, and we just had a log and a log on the left and the right, that would actually be perfect, because then we could equate what was inside the logarithms equal to each other. But dividing 2 to this side will not do that for us. Instead, we had that property that said if there's an exponent here, you can bring it down front. But you're allowed to reverse this too. You can say if there's an expression here or a number here, you can remove it and place it into this exponent. That's what I'm going to do on the left side of this equation. I'm taking this 2, and we're going to put it right here in the exponent. The left side is log of x squared is equal to log of 32. Now, since we have the logarithm on both the left and the right side, we can essentially cancel it. And that leaves us with x squared is equal to 32. If log of x squared is equal to log of 32, it's got to be that the thing in the logarithm is equal to the thing in this logarithm. So now we need to solve for x. Okay, let's see. I guess I'll take the square root of both sides. That seems like a logical next step. And when I do that, I get x on the left, but you get plus or minus root 32 on the right. And technically, I think you can reduce this. I'm thinking of like a perfect square that is inside of 32. And yeah, okay. So here we have x is equal to plus or minus 32 is 16 times 2. Having a perfect square under a square root when you have a product is nice because you can take the square root of these things separately. The square root of 16 is 4. Here we're not going to do anything to the 2. We're not going to take the square root of it at all. This is plus or minus 4 root 2. So the 4 because we are taking the square root of 16, but root 2 because we're not. We're just leaving it under the square root and doing nothing to it. So hey, it looks like we have 2 solutions, right? We have x is equal to the positive solution, which was positive 4 root 2, and also x was equal to negative 4 root 2. They both work, right? And the answer is no. We're actually not going to include this one, but we will keep this one. And what is the reason for this? If you focus on the original equation, there is log of x. What is the domain of the logarithm? What numbers are you allowed to put in place of x? And the domain was positive numbers. You can put any positive number that you want to in place of x. Like this one. I don't need the positive here, but 4 root 2. You can put this in here. And if you do, it'll make this equation true. But here, negative 4 root 2, you can't put into this. You can even check it on your calculator. If you put a negative number here and take the logarithm, it's going to say error because it's not a number in its domain. So for this problem, we had one answer, and that's it.